Wow, I'm so excited to be here to celebrate this really special event. I thought I would talk a little bit about how nature makes materials. I brought along with me an abalone shell. This abalone shell is a biocomposite material that's 98% by mass calcium carbonate and 2% by mass protein. Yet it's 3,000 times tougher than its geological counterpart. And a lot of people might use structures like abalone shells like chalk. I've been fascinated by how nature makes materials, and there's a lot of secrets to how they do such an exquisite job. Part of it is that these materials are macroscopic in structure, but they're formed at the nanoscale. They're formed at the nanoscale, and they use proteins that are coded by the genetic level that allow them to build these really exquisite structures. So something I think is very fascinating is, what if you could give life to non-living structures like batteries and like solar cells? What if they had some of the same capabilities that an abalone shell did in terms of being able to build really exquisite structures at room temperature and room pressure using non-toxic chemicals and adding no toxic materials back into the environment? So that's kind of the vision that I've been thinking about. And so what if you could grow a battery in a petri dish? Or what if you could give genetic information to a battery so that it could actually become better as a function of time and do so in an environmentally friendly way? And so going back to this abalone shell, one thing besides being nanostructured, one thing that's fascinating is when a male and female abalone get together, they pass on the genetic information that says, this is how to build an exquisite material. Here's how to do it at room temperature and pressure using non-toxic materials. Same with diatoms, which are shown right here, which are glaceous structures. Every time the diatoms replicate, they give the genetic information that says, here's how to build glass in the ocean that's perfectly nanostructured, and you can do it the same over and over again. So what if you could do the same thing with a solar cell or a battery? And so I like to say my favorite biomaterial is my 4-year-old. But anyone who's ever had or knows small children know they're incredibly complex organisms. And so if you wanted to convince them to do something that they don't want to do, it's very difficult. And so when we think about future technologies, we actually think of using bacteria and virus, simple organisms. Can you convince them to work with a new toolbox so that they can build a structure that would be important to me? Also, when we think about future technologies, we start with the beginning of Earth. Basically, it took 1 billion years to have life on Earth, and very rapidly they became multicellular. They could replicate, they could use photosynthesis as a way of getting their energy source. But it wasn't until about 500 million years ago, during the Cambrian geologic time period, that organisms in the ocean started making hard materials. Before that, they were all soft, fluffy structures. And it was during this time that there was increased calcium and iron and silicon in the environment, and organisms learned how to make hard materials. And so that's what I would like to be able to do, convince biology to work with the rest of the periodic table. Now, if you look at biology, there's many structures like DNA and antibodies and proteins and ribosomes that you've heard about that are already nanostructured. So nature already gives us really exquisite structures on the nanoscale. What if we could harness them and convince them to not be an antibody that does something like HIV, which was incredibly interesting talk earlier, but what if we could convince them to build a solar cell for us? And so here's some examples of some natural shells, natural biological materials, the abalone shell here, and if you fracture it, you can look at it, the fact that it's nanostructured. There's diatoms made out of SiO2, and they're magnetotactic bacteria that make small single-domain magnets used for navigation. So what all these have in common is these materials are structured at the nanoscale, and they have a DNA sequence that codes for a protein sequence that gives them the blueprint to be able to build these really wonderful structures. Now, going back to the abalone makes this shell by having these proteins. These proteins are very negatively charged, and it can pull calcium out of the environment, put down a layer of calcium and then carbonate, calcium and carbonate. It has the chemical sequences of amino acids which says, this is how to build the structure. Here's the DNA sequence, here's the protein sequence in order to do it. And so an interesting idea is, what if you could take any material that you wanted or any element on the periodic table and find its corresponding DNA sequence that coded for a corresponding protein sequence to build a